Hi, and welcome to my presentation on my master's thesis on numerical ray tracing of medium and high frequency radio waves in the terrestrial ionosphere. In its entirety, my thesis is an amalgamation of ionospheric plasma physics, computational electromagnetics, numerical analysis, and software engineering. But in this presentation, however, I will briefly cover the significance of the ionosphere for medium and high frequency radio physics, and summarize how special technique in geometrical optics is used in modeling radio wave propagation in these particular radio bands. By the medium and high frequency bands, I denote radio carrier frequencies in the range 0.3 to 30 MHz. Lastly, I will present how ray tracing can be used for a particular sample of applications in long-range telecommunications and spaceborne radio instrumentation, and what kinds of results we obtained in the context of my thesis. The Earth's ionosphere is generated by solar photoionization and various chemical reactions and transport processes, forming an intricate layered substructure at altitudes starting from roughly 100 kilometers above the ground. The F layer, shown here at an altitude between 2 and 300 kilometers, is a region that harbors the maximum free electron density. These electrons oscillate at the so-called plasma frequency at a few million times a second, which is why radio waves close to these frequencies are strongly refracted in the ionosphere. The ionosphere also exhibits significant diurnal variation. The dynamic nature of the ionosphere is visualized in this neat animation which I borrowed from NASA's Scientific Visualization Studio. The heat map represents the oxygen ion density at the 350 km altitude and can be seen to be the highest around noon at the equator. Also, this animation shows the low-altitude geomagnetic dipole field lines, a component we will find to play a very interesting role in ionospheric radio propagation. It is precisely because of the medium and high-frequency plasma oscillation that the ionosphere is an interesting subject for medium and high-frequency radio wave propagation. The electron plasma frequency takes values around 1 to 10 MHz in the Earth's ionosphere. The mathematical equations governing the EM wave propagation in the ionosphere are these as a partial differential equation shown here. Maxwell's equations relate the EM fields to their sources, whereas the last fluid momentum equation is needed for modeling the conductive properties of the medium. In fact, in this last equation we need one very important assumption to make the system solvable. The pressure divergence term is assumed to be insignificant due to low temperatures in the medium. This is known as the cold plasma approximation and will be a cornerstone in deriving the refractive properties from here forward. By assuming the EM waves to be small amplitude plane wave perturbations of the medium, the refractive index of the radio waves is given by the Appleton-Hartree equation shown here. I think this is a very interesting result because it shows that dispersion in the ionosphere is anisotropic. The refractive index depends on the propagation direction of the wave, as evidenced by the angle theta between the Bay vector k and the external geomagnetic field B0. This property has another interesting consequence, namely that there are two so-called characteristic propagating wave modes. These are known as the ordinary and extraordinary modes, and are distinguished by the plus-minus sign in the denominator of the refractive index. If the propagating radio waves are sufficiently high frequency, their trajectories can be modeled by first-order ordinary differential equations, much like in Hamiltonian mechanics for ordinary particles. These equations are to be numerically integrated in time to solve for the radio path. This is known as ray tracing. The function h in the ray equations is called the ray Hamiltonian, and is a constant of motion derived from the radio wave dispersion relation. Okay, so what can ionospheric ray tracing be used for? In what follows, I will present two use cases that were studied in my thesis. In long-range radio networks, the medium and high-frequency bands can be used to transmit hundreds or thousands of kilometers beyond the horizon. The maximum usable frequency, or MUF for short, is a characteristic property between two ground stations and is a vital engineering parameter for designing optimal transmissions. Using an ionospheric model and ray tracing, it is possible to predict the maximum usable frequency at a given time. The other application is in radio transmission inversion and the Suomi 100 satellite, to which I will get to in a bit. Let's see how the maximum usable frequency can be predicted. I have placed two ground stations 300 kilometers apart. The ionosphere is generated from the International Reference Ionosphere model at this particular time of year, time of day, and geographical location. What you're going to see is how the blue transmitter at the bottom left starts transmitting in all directions at a frequency of 5.5 MHz. The paths of all rays are solved by numerically integrating the Hasselgrove ray equations until the rays are outside the simulation domain. As the simulation proceeds, notice how the vertically transmitted rays just penetrate the ionosphere and escape into outer space. Most rays are reflected from the F flare towards the ground and can be received by the green receiver far beyond the horizon. Now let's try that again at a slightly higher frequency of 5.6 MHz. This time, a larger portion of the rays are not reflected. In a region extending to 300 km from the transmitter, no reflected rays are incident. This is known as the skip zone. The green receiver is situated at the very edge of the skip zone. If we increase the transmission frequency by any more, the skip zone becomes even larger. For 5.7 MHz shown here, the receiver lies inside the skip zone, and thus cannot receive signals from the blue transmitter. We have hence found that the maximum usable frequency between these two stations is around 5.6 MHz. To finish this presentation, I would like to talk about the possibility of radio transmission inversion as a space instrument analysis tool. The Suomi 100 satellite, of which a partially assembled engineering model is shown here, is equipped with a ferrite medium and high frequency antenna developed at Aalto University. The ferrite antennas are the slightly darkened depressions in the top white face of the satellite. Now, if the satellite can measure signals of a certain frequency received from a certain direction, one can figure out where the signal was transmitted from. This is possible because the ray equations are time invertible. By integrating them backwards in time, the radio transmission can be traced from the receiver back to the transmitter. I'll try to demonstrate this property in what follows. Let us imagine that a ground station is transmitting at 6 MHz. For a certain transmission direction, the signal is propagated to the satellite at a 575 km altitude. Next, I will turn the received wave around and integrate the ray path backwards. It can be seen that the ray traces its path back to the transmitter. If the used ionospheric model is accurate enough, this property can be used in data analysis to deduce the sources of the medium and high frequency signals received by the Suomi 100 satellite. Lastly, I would like to extend a special gratitude to my thesis supervisors, to Professor Esa Kallio at Aalto University School of Electrical Engineering, to Dr. Kirsi Kauristie at the Finnish Meteorological Institute, and Docent Heikki Vanhamäki at the University of Oulu. The Finnish Physical Society, thank you for providing me with the opportunity to prepare this presentation on my master's thesis. Thanks for watching, over and out.